This is a demonstration of my Peloton simulation. I call it Peloton 5.5. The modeling platform is NetLogo, and here we see a number of arrows that represent a peloton of cyclists. They do actually momentarily change into a form that looks a bit more like actual cyclists, but we're not concerned with the appearance of the cyclists here. What we're concerned with are the rules of behavior, the rules of interaction, or the principles of behavior that determine the collective behavior of the group. So before I actually run it, I'm going to just give you some sense of what features are involved in this model. So there are some variable sliders. For example, over here we have a variable slider called Peloton size, and it says 10, but that's actually per line, so I multiply that by 4, and there's actually 40 cyclists there. There's a number of graphs. There's a graph here that I call the power output, and it shows an output for a front rider, which is actually in this model fixed. I fixed the output of the front rider, but the drafting rate, or the power output of the drafting rider, is not fixed. It's variable. So the variable slider over here called drafting rate is what I use to change the drafting rate. So I can slide that up and down and change the drafting rate, which in turn alters the power output for the following rider, or the rider in the drafting position. So I have this graph called Peloton convergence ratio, and that incorporates the values of the front rider, the power output for the front rider, and the output for the drafting rider, which is a fraction of that of the front rider. And it also incorporates this value called the maximum sustainable output, which I'm not going to change here, but it is an element that will alter the fractional output of the drafting rider to the front rider, and which is another factor in this Peloton convergence ratio, which is key to the whole model, because I incorporate that equation, and this fractional output, the changing value of the Peloton convergence ratio, is what determines the behavior of the group. So before I get into that anymore, I'm actually just going to run the program. Now there are other features here that I'm not going to get into for the sake of brevity, but there's my group, and I'm going to run it. Okay, there they go. So what happens immediately off the start in this particular range of outputs is a rapid increase in density and fairly rapid positional change. We've just seen a small group break off, but basically what we see are sort of a bee-like behavior occurring among the group. So they're fairly free to move around, and they change position fairly rapidly, and they're in a high-dense situation. So one feature of this model that's quite important that I should mention is that basically I incorporate a principle that I believe exists within pelotons, and that is that there's inevitably, when you have this coupled behavior where there's riders behind that can save energy by drafting and have comparatively higher potential output, or they save energy, they have potential energy that allows them to be fresher, or to pass others with the ones in front with ease as the ones in front fatigue. So you have a principle of pelotons that says that you're going to have continuous, or there's an inevitability to continuous passing within the peloton, and that I model into this I've included that as a feature of this model. And so what happens is, at these low outputs, you have high positional change, because there's continuous passing going on, and then as you increase the power output, then the ability to pass falls. And we see this in pelotons. It's fairly apparent to anyone who's ridden in a peloton, and basically as the speed goes up, it just gets harder to pass. You slot into a certain position, and unless it drops below a certain speed, you basically have a lot of difficulty passing. You have to go flat out, if at all, if you can at all. But the principle is that as speed increases, the ability to pass falls, and that's something I've included in this model. So now we've seen the sort of this one extreme of behavior where there's it's at a low power output and a low Peloton convergence ratio. I'm going to drop down the drafting rate to so that we get to a high Peloton convergence ratio. And I'm talking really fast because I want to get through this without everybody getting bored to tears. So what we see here are very rapid shift in the Peloton behavior, and it begins to stretch out, and it's actually splitting up quite a bit. But really what we're interested in here, what I want to show, is sort of the stretching behavior that occurs, and that is what we see in Peloton when the speed begins to increase and riders have more difficulty passing. The Peloton naturally begins to stretch, and that's what we're seeing in this phase here. So that we can call that a phase of Peloton behavior, and the underlying principles are what I'm modeling here. The principles of dropping capacity to pass, increasing power output, and the relationship between the maximum sustainable output and the fractional output of the drafting rider to the front rider, as I show here, and which is reflected in this value called the Peloton convergence ratio. So now we're looking at the one extreme of this stretched behavior and relatively low passing behavior occurring. Now what happens if we throw the drafting rate into a mid-range? Slow them all down. Drafting makes it easier for the following rider to follow, and the power output to maintain the pace of the front rider fall. So that gives us a mid-range of Peloton conversion ratio of 0.49 here. So what we actually will begin to see are oscillating behavior, oscillations between phases in this mid-range. We see a rapid shift or potential for change at unpredictable times between the stretch state and the higher density sort of rapid positional change state. So here we see right now are little groups that are more stretched out, but if we watch for long enough we will see them collapse, or this one up here is sort of beginning to collapse into a higher density condition. But we will also see not only oscillations, but we'll see simultaneous behavior. So we'll see one group or another collapse into a higher density state while another one stays stretched out. And so what this indicates is that it allows us to make a prediction that in actual pelotons, in this mid-range of power outputs, we will see sort of a sensitive condition, or the power output is sensitive to change between the two states. And that's interesting because it's not actually something I necessarily predicted when I began modeling this. I was aware of the different phases and that the different power outputs determine the patterns of behavior, the manifestations of the behavior, and the phases that we see. But I didn't actually necessarily predict that we would see sort of this oscillating behavior in the mid-range. So what it suggests is that, well, we actually need to go to an actual peloton or a whole bunch of pelotons and get data where we can analyze it and look for this mid-range of power outputs in which it's sensitive to changing between the two sort of manifestations of behavior. So there we see this one all stretching out again when it was just before it was in a higher density situation. So another thing that this allows us to make a prediction about is about other natural systems, and so we can ask the question at least, and if this model is based on sound principles, and I don't for a second deny the possibility that somebody will come along and say, well, no, you actually what you've modeled here cannot actually reflect reality. I mean, you are showing some behaviors that look somewhat realistic, but there's enough flaws in it that it's not representative of actual pelotons. So that's the nature of science, of a scientific endeavor. Ultimately, is that you're going to present something, a finding that you present evidence for a certain theory or hypothesis, but that can be overturned by other findings or new evidence or a new model, a better model. And there is another model out there that I'm going to demonstrate. I'm going to show as well, and I'm going to draw a few comparisons, but I'm not going to get into it at this point. They're a model by Eric Radomero that he recently had presented at a conference, which I'm going to discuss later. But here we have, my model shows this oscillating behavior, and it allows for a prediction within actual pelotons for this oscillating behavior, sort of this duality of states at this mid-range of peloton convergence ratio. So it's this duality of states it means that it's sensitive to changing between these two states. So we can make the prediction that in other types of systems we may see this occur as well. So that's in a nutshell my Peloton model 5.5. Thank you for listening.